Hello, physics students. Now today we're going to begin a new topic called magnetism. Magnetism is a very broad, long topic that we could spend months or even years studying. But it turns out that in the Regents curriculum, it's been shortened down quite dramatically so that we're going to spend maybe 2 videos on this topic, 3 tops. So let's begin. What I have here are a couple iron bars, and I'm going to magnetize them by putting them in this magnetizer. I'm going to put this end this way, this end that way, connect them with this little bar here, and then I'm going to hit a button here a couple times. And what I've done is I've now created some permanent magnets, which you could see they lift up these paper clips. Just a little point we could make right away is that this magnetic force is like the electrical force. It's much stronger than the gravitational force we studied earlier in the year. These paper clips are pulled down by every piece of matter in planet Earth. The core, the oceans, every mountain is pulling these paper clips down with the force of gravity. It takes that much mass to create this much gravity. One small bar magnet and it easily wins against the entire Earth. Another thing that we're going to study is that magnets interact not just with pieces of iron, they also interact with each other. So again, remember, this is the north end, this is the south end. If I bring the south end of this magnet here and I let go, you could see that the south and south repel each other. Same with north and north. They repel each other. So it was like in circuits, electricity, positive repel, negative repel, same with the poles. But if I bring opposite poles next to each other, well, you could see right away there's an attraction between the north end and the south end of this magnet. And then if I go this, north and south here also attract. So that's the first thing that we're going to put on the board, the notes of magnet-magnet interactions. So you just saw 2 magnets interact with each other. Here's the pattern. Magnet-to-magnet force, if you have a north next to a north pole, those magnets will repel. If you have a south next to a south, those will also repel. But if you have a south next to a north or a north next to a south, you'll get an attraction. But where did this magnetic effect come from? The source of magnetic field is the atoms themselves. So as you know, atoms are made of protons and electrons. Protons are in the middle like the nucleus of an atom, and around orbit the electrons. So because the electron orbits around, it's an electric current, and in other physics courses you would learn that electric currents create magnetic fields. So an orbit of an electron has a magnetic field that it creates or generates coming through the atom. But the electron itself also has something that's considered to have a spin. So it's spinning like the Earth is spinning on its axis. And because it's a negative charge spinning, that also creates a magnetic field. So the source of the magnetic field comes from spinning and orbiting electrons in an atom. So let me create a pause to give you a chance to copy these notes down. All right, so then why isn't a piece of paper magnetic? It's also made of atoms, protons, electrons orbiting and spinning. Only certain materials like, so first of all, most matter, the magnetic effects of the individual atoms and the individual electrons are random. In other words, the magnetic field of all the atoms tends to go every which way, so the random magnetic field orientations tend to cancel, so the overall larger object has no net magnetic effect. But in something like iron, you can magnetize it, like when I put it in that magnetizer and hit the button. What happens is it takes these atoms or these electrons and it aligns them and takes away their randomness so that they tend to point all in one direction. So the atom's magnetic fields now are more or less aligned. It doesn't have to be a perfect alignment. And then what we say is that the end where the magnetic field's coming out, we consider that the North Pole. Where the magnetic field's going into these atoms, it's considered the South Pole. But some notes. Heating or banging an atom can unalign the atoms. So once you get them aligned, if you take a piece of iron and put it in a blowtorch, the magnetic effect goes away. Another thing, a lot of people don't realize that every single magnet has to have two poles of equal strength. It's actually a law of nature. And you might be thinking, why? Why don't I just cut off this magnet and I'll have a north end here and a south end here? It doesn't work that way. What happens if I cut these into two separate magnets, then these ends will then become the north pole of these atoms, and these ends right here tend to be the south pole of this magnet. So what I have are two permanent magnets, each with their own north-south poles. Okay? So let me return the notes to their original form. And I'll create a pause to give you a chance to copy these notes down. Okay, so next thing I'm going to talk about is diagramming the magnetic field around magnets. As you already saw, opposite poles attract, right? So, and like poles repel. Now we could utilize or take advantage of that property to map what we call the magnetic field around a bar magnet. The way we could do that is we can make one of the magnets very small compared to the other one. And then what we can do is take this small magnet that's free to rotate and move it around this other larger magnet, and that smaller magnet, you might notice, turns in different directions at different places around this bar magnet. So what I'm doing is getting a feel for the direction of the magnetic field around this bar magnet. I also can do that with many, many little magnets with this little device here. And you see here I've got one large bar magnet in the middle inside this plastic frame. And all around it are little tiny magnets that are all free to rotate. I don't know if you could see this, but if I try and take the alignment away here and let it go, it goes back to the alignment with the magnetic field. So this shows me the pattern of the magnetic field around a bar magnet. Okay, so we can have other shaped magnets too. There's something called a horseshoe magnet. All it is a bar magnet that's been bent into a shape of a horseshoe. It still has a north and a south pole. So this would be, one end would be north, the other one south. And we can use a similar device or similar method with a compass, moving this around and mapping the magnetic field. Or we could look at this device. I've got to be careful so it doesn't fall out. And it shows the pattern of the magnetic field around a horseshoe magnet. Okay, so you see the field lines sort of curving around like they did in the bar magnet, but just from one pole to the other between these two bent poles. So what I'm going to do now is go to the board and show you how you can sketch these magnetic fields, the patterns, using some very basic rules. So here's how you can create a diagram summarizing that information you just saw. So we got a north and a south pole, and I drew the field lines coming out of north going into south, but here are some important rules. Again, the lines always come out of north and into south, but you must have the same number of lines coming out of the north pole as into the south pole. Every single magnet in the universe has two equal strength poles. You can never find a magnet that has a stronger north pole or a stronger south pole. The poles are equal strength. So if you have a weak north pole, you got to have a weak south pole also. And you could never have a north pole or a south pole alone. Never can happen. And the lines can never cross because, again, these lines represent the net magnetic field. So the equal number of lines, notice I have 1, 2, 3, 4, 5, 6, 7 lines coming out of north, 1, 2, 3, 4, 5, 6, 7, going into south. Must be. If I had 8 here, I better make 8 over there. So students get very sloppy. They say, oh, magnetism, easy topic, and they just start sketching lines all over the place and they don't make the poles equal. They lose credit. Another thing that they do when they get into a hurry or maybe careless is they start going like this. And they make the lines either coming out of one point or going into one point. These lines cross. They cannot cross anywhere on this diagram. There has to be gaps everywhere, even near the magnet. So be careful of those points. All right, so let me create a pause to give you a moment to copy these notes down. All right, the horseshoe magnet. So it's shaped like this, like a horseshoe. There's a north and a south pole. The field lines come out of north into south, so they kind of go straight across in the region between the horseshoe bar here, and then they curve elsewhere. But again, if you tallied up all the field lines coming out of the north, they equal the same amount going into the south, and the lines also never cross. Another thing that we do often in experiments is we use these little compasses to map the magnetic field around a bar magnet, as I did, but in just a little bit more detail. So, for example, if I put a little compass here, you need to know that this compass will align itself, not pointing at the south or away from the north, but align itself with a magnetic field like that. And if I put a compass here, well, that one's easy. It'll just align. So we use little arrows to indicate the way the compass points. One over here will point toward the south pole, and maybe one over here. So when you see these circles on a test, you might want to sketch in the magnetic field lines and then draw in the appropriate arrows when it comes time to answer the question. All right, so let me create a pause to give you a chance to copy these notes down. Okay, next thing that I'm going to do is sketch the magnetic field around pairs of magnets. So, what I mean by that is, well, suppose I had a magnet like this, a north and a south pole, and over here I had another magnet that was a south pole and a north pole. Now, field lines, when a magnet's alone, they come out of north and go into this south over here. But what will happen, or what could happen instead, is they are drawn instead into the south pole of the other magnet. So I'm going to draw a few field lines, but I still have to follow the same rules that I did before. The lines can't cross. And now that I have 5 field lines coming out of this north, I've got to have 5 going into this south pole. So maybe I'll draw some field lines in like this. There's 3. I'm still short. Maybe I'll go like this. There. Now I have 5 and 5. But this magnet also is now lacking 5 lines because I have 5 going into south. I got to have 5 coming out of the north. So I could do one like this, 3. Now I need 2 more, so maybe I'll go like this. There. Now this satisfies all the rules. Out of north into south out of north, equal, 5, 5, 5, 5. Another possibility is if we have 2 magnets that are close to each other, but they're north poles. Now what will happen is these north poles will send field lines out, but they can't cross, so they'll tend to curl away rapidly toward their own south poles. Maybe I should have made this more like asymmetric, I think. All right, so I had 4 lines here, so I'm going to make 4 lines there, 4 here, and 4 there. Okay? So if you need a moment to catch up, I'll create a pause so you could copy those down. All right, one last one for pairs. What if we had 2 south poles together? Well, it's similar to this one. Now these field lines come in, but these come in so they can't cross, so what has to happen is something like this. Oops, wrong way. The arrow goes into south. Almost made a mistake. Again, 4 and 4. They don't cross anywhere. And the same thing has to be done here. So, south, south. Now, a lot of times on these tests, they won't show you the whole magnet. They'll show you like this, maybe as an example. And they don't show the south poles of either magnet. And in that case, you just do some arrowheads like this. So that's what you would do in a case like that. All right, let me create a pause to allow you to copy this down. Okay, so I want to also show you one other thing about magnets that can turn. So let me reconfigure the camera again. So a magnet that's free to swivel will align itself with the magnetic field that it finds itself in. But this magnet is also free to swivel. And if I turn this like this and let it go, you will see that it gets pulled back to its original orientation. And if I go the other way, 90 degrees, and let go, again, it gets pulled back to its original orientation. Even if I flip it around, almost opposite, again, it comes back to that original orientation. And that must mean that in this vicinity, there is some magnetic field, but there's no other magnet around here. Well, obviously, as you no doubt know, the Earth itself has a magnetic field. So this magnet is aligning to the Earth's magnetic field, which is looking like it's pointing in this general direction. So the reason for that is that the Earth itself is like a giant magnet. Let's see, let me move this here. So people long ago figured out, hundreds of years ago, centuries before, that if they were in the middle of the ocean and they had this, an object that was magnetic and free to rotate, it would point in this general direction like this. And since this end tended to point somewhere near the North Pole, by the way, it's not exactly near at the North Pole, it points somewhere, I think at this point, somewhere around here. And the place that compasses point toward actually moves through history. You could look it up online and you could see that this pole of the Earth moves around in this general vicinity. But since this tended to point toward the North Pole, logically they labeled this the North Pole of the magnet because it pointed to the North Pole. And this the South Pole because it pointed to the South Pole. And that makes sense, right? Unfortunately, it was wrong in a sense. It made an inconsistency. Because now we know that opposite poles attract. And so if you call this the North Pole of this bar, that must mean up here is the magnetic South Pole of the Earth. So even though this is the geographic North Pole, it's magnetically the South Pole of the Earth. Again, that came about because people didn't understand what magnetism was when they started labeling these magnets. But nonetheless, this is the magnetic South Pole. The magnetic North Pole is at the geographic South Pole or near it. And so the Earth itself, a giant magnet, similar to, oh, I moved it over here. Similar to this, you know, the planet Earth, and we've got, you know, this is the geographic North Pole, geographic South Pole, magnetic south, magnetic north, and the pattern of the magnetic field around planet Earth, if this were like a ball in there, would look something like this. So now what I'm going to do is I'm just going to sketch the pattern of the Earth's magnetic field on the board. So this is a diagram of what I just talked about with the globe. We got the Earth here. Here's what I don't want to say the South Pole. It's where Antarctica is, which is the magnetic North Pole of the Earth. Up here, I don't want to say the North Pole because it's actually the magnetic South Pole of the Earth. And the magnetic field lines come out of the north and go into the south. And everywhere on the surface of the Earth, there's a magnetic field. So go ahead and copy that into your notebook. Now, I should say that also mention that the Earth's poles do shift every few million years. So in the next few thousands of years, you never know. This might become north and this might become south to align with the geography. So it does naturally happen because of stuff happening in the core of the Earth, the molten lava. So that's magnetism. The first day we talked about magnet-magnet interactions, how magnets even get their magnetic properties from the electrons orbiting and spinning inside, and then when you align them, you get a permanent magnet. And we learned how to diagram magnetic field around bar magnets, horseshoe magnets, around planet Earth, around pairs of magnets. So we learned a lot of little things, quick things about magnets. I hope you enjoyed the physics. I hope you enjoyed the video. I'll see you in the next physics video.